So welcome everyone to today's lecture on thermodynamic cycles. Today we are going into a fascinating topic that underpins much of the modern engineering from the car engines to power plants. A thermodynamic cycle is a sequence of processes where a system like a gas or a fluid undergoes changes in pressure, volume, and temperature, ultimately returning to its initial state. Think of it as a loop where energy is transformed in useful ways. Why does this matter? These cycles are the backbone of heat engines, which where the powers, which power vehicles and refrigeration systems which keep our food cold. They are also critical for generating electricity in power plants. Throughout this lecture, we will explore different types of cycles, their efficiencies, and their real-world applications. We will look at power cycles like those in jet engines and heat pump cycles used in air conditioners. You will see how these cycles are analyzed using diagrams such as pressure volume plots to calculate work and efficiency. For example, the work output of a cycle is represented by the area enclosed in a PV diagram. And the power is simply that the work multiplied by how much cycles occur per second. By the end of this lecture, you will understand how this cycle converts energy and why they are so vital to technology. We will also touch on fundamental laws like the first and the second laws of thermodynamics that governs this process. So let's get started with an introduction to thermodynamic cycles and build our foundation for the exciting details ahead. Let's begin with the basics of thermodynamic cycles. As I mentioned, the thermodynamic cycle involves a system like air in an engine undergoing a series of processes such as compression or heating and returning to its starting point. This loop is key because it allows continuous energy conversion, making cycles essential for devices like heat engines, refrigerators, and power plants. Heat engines, for instance, convert thermal energy into mechanical work, powering everything from cars to turbines. Refrigerators, on the other hand, use work to move heat from a cold space to a warmer one. We categorize cycles into two main types: power cycles and heat pump cycles. Power cycles like the Otto cycle in gasoline engines or the Rankine cycle in steam power plants focus on producing work from heat. Heat pump cycles such as vapor compression cycles in your refrigerators transfer heat against its natural flow. A great example is the Otto cycle, which drives internal combustion engines in cars. To analyze these cycles, we use a pressure volume or PV diagram. The area inside the cycle loop on this diagram represents the net work done. The power output is then calculated by multiplying that work by the cycle frequency like engine RPM. Understanding this cycle helps engineers to design more efficient machines, saving energy and reducing cost. Today, we will explore how these cycles operate, their efficiencies, and their diagrams. By grasping this concept, you will see why thermodynamic cycles are the heart of energy systems we rely on daily. So let's move on the key concepts that makes these cycles. Now, let's see the core principles behind thermodynamic cycles. First, these cycles are closed loop, meaning the system, like a gas or steam, returns to its initial state after completing all process. This allows the cycle to repeat indefinitely, producing consistent work or heat transfer. The first law of thermodynamics is our starting point. It states that the net heat added to the system equals the work done, or the Q net equals to W net. In simple terms, energy in equals energy out, accounting for heat and work. For example, in a car engine, the heat from burning fuel produces work to move the pistons. Next, the second law of thermodynamics comes into play. It tells us heat naturally flows from the hot to the cold regions, and no cycle can be 100% efficient. The Carnot efficiency sets the theoretical maximum efficiency, limited by the temperature difference between the heat source and sink. To visualize these cycles, we use two key diagrams, the pressure volume or the PV diagram and the temperature entropy or TS diagram. The pressure volume diagram shows work as the area enclosed by the cycle path. Think of it as the push to the systems. The TS diagram highlights heat transfer and efficiency through entropy changes. These tools help engineers to analyze performance and optimize designs. For instance, a power plant efficiency depends on minimizing energy losses shown in these diagrams. Understanding these laws and diagrams is crucial for grasping how cycles convert energy effectively. Next, we will explore specific power cycles and how these concepts apply in real-world systems like engines and turbines. Now we will shift to the power cycles, which are all about converting heat energy into mechanical work. These cycles are the heart of systems like car engines, power plants, and jet turbines. So what is their main goal? To take the heat from a source like a burning fuel and turn it into useful work, such as spinning a turbine or moving a piston. There are several key power cycles we will cover today. The first is the Otto cycle, which powers gasoline engines in most cars. Then the diesel cycle, used in trucks and heavy machinery for their durability. The Rankine cycles, which drives the steam power plant like those in the coal or nuclear facilities. Finally, the Breton cycles runs the gas turbines and the jet engines propelling the planes and generating electricity. Each cycle has a unique process, but they all aim to maximize the work output. We measure their performance with efficiency, defined as the net work output divided by heat input, which equals W net divided by Q in. Higher efficiency means less wasted energy, which is critical for cost and environmental reasons. For example, a more efficient Otto cycle in a car means a better gas mileage. These cycles are analyzed using PV diagrams where the enclosed area shows the work done. Later, we will see how the Otto cycle 4-stroke create this loop. Understanding The power cycles help the engineers to design machines that do more with less energy. Think about the spark ignition engine in a car versus the ideal Otto cycle. We will compare those to highlight the real world challenges. Up next, we will contrast this with the heat pump cycles and explore how they move heat instead of producing work. Now we will explore heat pump and refrigeration cycles, which do the opposite of power cycles. Instead of converting heat to work, these cycles use work to transfer heat from a cold region to a warmer one. Think of your refrigerator or air conditioner. Their purpose is to move the heat against its natural flow, which requires energy input, usually electricity. The most common example is the vapor compression refrigeration cycle found in fridge, freezers, and AC units. It uses a refrigerant that evaporates to absorb heat from a cold space and condense to release it elsewhere. Another type is the absorption refrigeration cycle, often used in industrial settings or off-grid systems. To measure performance, we use the coefficient of performance or COP. For a heat pump, COP is the heat delivered to the warm space divided by the work input. For a refrigerator, it is the heat removed from the cold space divided by the work input. A higher COP means a better efficiency. Your fridge uses less electricity to keep food cold. For example, a modern AC unit might have a COP of 3, meaning it moves 3 times more heat than the energy it consumes. These cycles rely on components like compressors and evaporators, and we analyze them with the PV or TH diagrams to optimize performance. In a fridge, the cycle keeps the inside cold while dumping heat into your kitchen. Understanding these cycles is key to designing energy-efficient cooling systems, which are vital for comfort and food preservation. Next, we will zoom in on the Otto cycle to see how a specific power cycles work in gasoline engine. Let's take a closer look at the Otto cycle, which is the powerhouse behind gasoline engines in cars. This cycle is named after a scientist named Otto, which makes your car to go. It's an air standard cycle, meaning we simplify it by assuming air is a working fluid. The Otto cycle consists of 4 distinct processes. The first consists of isentropic compression process, where the piston compresses the air-fuel mixture, raising its pressure and temperature without heat loss. Second is the constant volume heat addition. The spark plug ignites the mixture, adding heat rapidly at constant volume, spiking the pressure. The third is the isentropic expansion or the power stroke. The hot gases expand, pushing the piston to produce work. Finally, the constant volume heat rejection, where the exhaust valve opens, releasing the heat as the system cools back to its starting state. The efficiency of the Otto cycle depends on 2 factors. The first one is the compression ratio, which is how much the mixture is compressed, and the gamma, which is the specific heat ratio of the gases. The formula is 1 minus 1 over r to the power gamma raised to minus 1. Now here, the higher compression ratio means a better efficiency. But there's a limit to avoid engine knocking. We visualize this cycle using PV and TS diagram. On PV diagram, we enclosed loop shows the work output, while the TS diagram highlights the heat transfer. In real engine, factors like friction reduces the efficiency compared to ideal cycle. Understanding the Otto cycle helps the engineer to design engines that balances power efficiency and emissions. That is why your car gets better mileage with modern designs. Next, we will explore the Rankine cycle, which powers massive steam plants. Now, let's see the Rankine cycle, the workhorse of steam power plants. Think coal, nuclear, or geothermal facilities. This cycle is crucial for generating most of the world's electricity. Unlike the Otto cycle, the Rankine cycle uses the water and steam as its working fluid. It consists of 4 main processes. The first is isentropic expansion in a turbine. The high pressure steam expands, spinning the turbine to produce work. This is where the cycle generates electricity. The second is the heat rejection in a condenser. The steam cools and condenses into liquid water, releasing heat to environment, often the cooling towers. The third is the isentropic compression. In the pump, the liquid is pressurized, requiring a small amount of work input. Finally, the heat addition in the boiler. The water is heated and vaporized, turning back to high pressure steam to restart the cycle. The efficiency of the Rankine cycle is calculated as the net work output, that is the turbine work minus the pump work divided by heat added in the boiler. To boost the efficiency, the power plant superheat the steam or reheat cycles, but the losses like heat rejection limit performance. We analyze the cycle with the PV and TS diagrams, where the TS diagram shows the heat transfer clearly as the steam change phases. In coal plants, for example, burning fuel provides the boiler heat, while the condenser cooling water absorbs waste heat. Understanding the Rankine cycle helps engineers to optimize power plant for efficiency and sustainability, reducing fuel use and emissions. It is a cornerstone of modern energy systems. Up next, we will look at the Brayton cycle, which powers the jet engines and the gas turbines. Now let's see the Brayton cycle, which powers gas turbines and jet engines. Think of airplanes which are moving in the sky, or the turbines which are generating electricity. This cycle uses air as a working fluid and operates at high speed, making it ideal for aviation and power generation. The Brayton cycle has 4 key processes. The first is isentropic compression in a compressor. The air is drawn in and compressed, increasing its pressures and temperatures. This takes work input like squeezing a balloon. Second is the constant pressure heat addition in a combustor, where the fuel is burned, heating the air at constant pressure and significantly raising its temperature. The third is the isentropic expansion in a turbine. The hot, high pressure gas expands, spinning the turbine to produce work, which powers the compressor and the external loads like a generator or jet thrust. The fourth is the constant pressure heat rejections. The exhaust gases releases heat to the surrounding, cooling down before the cycle repeats. The efficiency of the Brayton cycle depends on the pressure ratio P1 over P2 and the gamma, which is the specific heat ratio. A higher pressure ratio improves the efficiency, but there are certain material constraints that must be considered for the turbine which can operate or run. The PV and TS diagrams help us to analyze the cycle. With the PV diagram showing the work as the enclosed area. In a jet engine, the exhaust momentum produces thrust, while in a power plant, the turbine drives a generator. Understanding the Brayton cycle is the key to designing efficient, powerful systems for energy and transportations. Next, we will explore how the TS and PV diagrams visualize these cycles. Now let's look on the tools such as TS and PV diagrams to analyze thermodynamic cycles. The TS and PV diagrams are the X-rays of engineering, revealing how cycles work and where energy flows. The first, the temperature entropy, or the TS diagram plots temperature against entropy, which measures disorder in the systems. In a TS diagram, the heat transfer appears as the area under the curve. For example, in the Rankine cycle, the TS diagram shows the heat added in the boiler as the large area during vaporization. It's also great for spotting efficiency losses as entropy increases with irreversible processes like friction. A Carnot cycle, the gold standard of efficiency, forms a neat rectangle on a TS diagram, highlighting maximum heat to work conversion. Now, the pressure volume or PV diagram is the go-to for the work calculation. Here, the area enclosed by the cycle loop represents the net work done. In Otto cycle, for instance, the PV diagram shows the compression and expansion strokes clearly, with the enclosed area equaling the engine's work output. These diagrams are especially common for internal combustion engines, where the piston moves in a defined volume. By comparing real and ideal cycles on a PV diagram, engineers can identify losses like the heat escaping in an exhaust. Both diagrams are complementary. The TS focuses on heat and efficiency, while the PV emphasizes work. Together, they help to optimize system, whether it's a car engine or a power plant. Mastering these tools lets you to see energy transformations, making cycle analysis intuitive. Next, we will look at the real-world application of these cycles in the power transports and the cooling systems. Let's connect thermodynamic cycles to the real world, where they power our lives in a countless way. First, power generation relies heavily on these cycles. The Rankine cycle drives thermal power plants, that is coal, nuclear, or geothermal, converting heat into electricity like lights our home. The Brayton cycle powers gas turbines, often used in combined cycle plants for efficient, flexible production. These cycles are critical for meeting global energy demands, while the engineers work to boost their efficiency and cut emissions. Now let's talk about transportation. The Otto cycle is the heart of gasoline engines powering most cars on the road. Every time you hit the gas, the Otto cycle four-stroke delivers power to the wheels. The diesel cycle, meanwhile, runs heavy-duty vehicles like trucks, buses, and ships, prized for its efficiency and durability under tough conditions. These cycles keeps goods and people moving globally. Finally, the refrigeration and air conditioning depends on heat pump cycle, especially the vapor compression refrigeration cycle. This cycle keeps your fridge cold, your office cool, and even chills industrial process like food storage or data centers. Without it, the modern life from grocery stores to the summer comfort would be unthinkable. Each application shows how thermodynamic cycles transform energy to meet specific need, whether it's work, motion, or cooling. By studying these cycles, engineers design systems that save energy, reduce cost, and lessen environmental impact. For example, improving a car's auto cycle efficiency cuts the fuel use while optimizing a fridge COP lowers your electricity bills. These applications highlight why thermodynamic cycles are engineering unsung heroes. Up next, we will wrap up why these cycles matter for the future. Now, let's reflect on why thermodynamic cycles are so fundamental. These cycles are the invisible engines behind energy conversion systems, from the car's Otto cycle to the hum of a power plant's Rankine cycle. The power cycles like Bretons and diesels turn heat into work, driving turbines, jets, and vehicles that power our world. Meanwhile, refrigeration cycles like vapor compression defy nature by moving heat from cold to warm, keeping our homes comfortable and food fresh. Understanding this cycle isn't just academic, it's about solving real problems. By analyzing PV and TS diagrams, engineers calculate work, heat, and efficiency, finding way to do more with less energy. For instance, boosting a Rankine cycle efficiency in a power plant cuts fuel cost and emissions, while a better Otto cycle means cars that go farther on a tank. The first and second law of thermodynamics remind us that the energy transformation have limits, but they also inspire innovations like hybrid engine or advanced refrigerants. These cycles connect theory to practice, helping us to design systems that are sustainable and efficient. As the energy demand grows and the climate challenges mount, the thermodynamic cycle will play a steering role in creating cleaner technologies. Think of electric vehicle chargers powered by the efficient turbines or the eco-friendly cooling systems. I hope this lecture has shown you how these cycles shape our world and spark your curiosity to explore further. For homework, try sketching PV diagram for the Otto cycle and calculate its efficiency for a given compression ratio. Let's keep pushing to understand and improve the systems that power our lives. Thank you for your attention, and I will see you in your next class.